Thank you very much. Thank you very much to everybody for being here, joining my presentation. Well, I'm from the Institute of Railway Engineering and Transport Economy in Graz. This is in the south of Austria. It is a very small city, so don't mind if you don't know it. Our main expertise at the Institute is railway asset management, and we deal there mainly with track recording data and carry out strategies, maintenance strategies, renewal strategies for railway tracks based on economical and technical aspects. So what I'm going to present today is fiber optic sensing. We use already installed cables alongside a railway track in Switzerland, which is a very dense network, and we try to use it for railway asset management, and in this special case for railway track condition monitoring. First of all, there were no changes made on the cable routing, on the track layout, or something like that. We just took this fiber optic cable as it was there in the cable trough and connected it with the interrogator. We have two interrogator units, and we are able to monitor more than 40 kilometers of track. But first of all, what do we do at the Institute, and why do we do that? Well, railway track is a very expensive asset, and the overall aim of every infrastructure manager is to achieve a very long life cycle. You can do that if you maintain your asset properly, but the asset life, the service life, depend on two things. First of all, the load, the traffic volume. High traffic volume means high wear and tear, faster deterioration of the components, such as ballast, sleepers, rails, and so on and so forth. And second, the maintenance strategy. If you do a predictive maintenance strategy, preventive maintenance strategy, or a reactive one. So you have some data, you have three things to consider to come from data to maintenance and to renewal strategies. First of all, input. Of course, exact position data. Everyone would say, yeah, that's obvious, but it is not. With our partners, several infrastructure managers in Europe, they gave us some data and said, oh, it's very good positioned. No matter, you can just make some analysis. We check it, and it is not very good positioned. So there are, I don't know, there's an offset of a couple of meters, 10 meters offset of one point to the other. And they said it's the same point we've measured. So, no, it's not. The next thing is periodic condition evaluation. In order to carry out time series analysis, if you evaluate your track once a year or 2 times in 10 years, this is not periodic. A track deteriorates and you have to maintain it. And of course, as it deteriorates, we have to guarantee that it don't exceed certain thresholds. On the one thing, because of the safety, and on the other thing, because of the driving comfort. If you have all these data, you can analyze it, you can make time series analysis and prognosis of your assets. In theory, the best thing is you get a condition-based wear prognosis, and you can carry out maintenance demands for every specific section. One of them needs a renewal, one of them needs a maintenance. The right maintenance strategy at the right point in time. And there, of course, are some sections which do not need any intervention. So what are the data infrastructure managers have to evaluate a track? One thing is the track recording vehicle. I think every infrastructure manager has it in-house or has it outsourced, but have it, and it measures the track, depends on the length of the network, 2 to 4 times a year, and delivers data about the vertical alignment, the gauge, the inclination, and so on and so forth. At specific points in the network, infrastructure managers have also wayside train monitoring systems. They measure the condition of trains, such as out of roundness, the loading, and of course wheel flats. In Austria and in Switzerland, we have about 5,000 kilometers of main track and 13 or 15 of these WTMS systems. So as you see, it's not a quite dense network for the WTMS. And smart sensors have become very popular over the last few years. You can equip nearly every asset with a smart sensor, like a turnout, like a bridge, with a smart sensor, and they deliver data for each train pass. And why should we use fiber optic sensing? Well, we have critical assets like turnouts, like some specific points on the track, like white spots, hollow sleepers, hanging sleepers, which we cannot measure with the track recording car or other things. We have to take care of our stuff, which goes outside and make a visual inspection. So fiber optic sensing, in this case, is able to derive continuous and permanent track monitoring for the entire network. In Switzerland, they have more than 9,000 kilometers of fiber optic cables installed alongside the track. So as you see, there's a huge potential for this. Within an optical fiber, there are various scattering processes. I'm not going too much into detail of that. Some of you are aware of this, and you can read it in the paper. So, 3 scattering processes, which can be divided into spontaneous, stimulated, elastic, inelastic, linear, and nonlinear processes. Most of them, the main difference is the different amplitudes and the different frequency shift. We are going to focus in this work on the Rayleigh scattering for distributed acoustic sensing. So this relies on the Rayleigh scattering, and within each fiber there are minuscule impurities. And if you couple in a laser pulse, it will scatter. You will get some backscattered light. And when an event takes place on the track, this backscattered light is changed, and the interrogation unit reconstructs the signal and gives you information about the event which took place on this point. So you can think of this about thousands of sensors, equidistant distributed of 10 meters, which monitor the events taking place on the track. One thing is availability of railway tracks. This measurement principle has no influence on it. If our staff goes out and has to inspect, turn out a bridge, you have to close the track, or you have to derive slow orders because of the safety. With this technology, we're able to monitor every train pass over the whole network. So the first thing you get when you do this, when you analyze the data, is a waterfall diagram. I'm pretty sure some of you have seen something like this. On the x-axis, you can see a track kilometer. Actually, this is the result of the interrogation unit 1, which covers more than 27 kilometers of track and 20 minutes of recording. The color represents the acoustic intensity. Blue means a very low acoustic intensity, and red a very high one. So as you can see here, the train travels in this direction, and at this part, the color is yellow. So why is that? Well, we think it's because the train uses the second track. It's a double track, so the intensity of the signal is below the signal when the train uses the first track. So the waterfall diagram is very good for train traffic monitoring. As you can see various train times, and you can distinguish between, and you can see the duration of stops in stations. As you can see here, here's a station here. And of course, as we've made no changes of the fiber optic cable, we also have coils. Coils are a reserve. If the cable breaks, you can splice it together, so you don't have to install it again. Next thing is, you can see the traveling speed of each train. If it's a freight train, or short commuter train. And as we can see that, we also can see the braking process. So this enables for timely customer information, and you can see every train delay in real time. And what do you think is that? It is a motorway which is parallel to the track. You can see the influence of the cars the whole time. So when we can distinguish between various train types, the question is, can we also distinguish between track sections, good condition, bad condition, various assets? Well, when you do that, you have to dig deeper into the data. Carrying out a spectrogram, which is a visual presentation of the spectrum of a signal. As the signal varies over time, you can see a train that passes a worn-out insulated rail joint. So if you can think, you have a steady, smooth ride over the track, and then you pass a rail joint, which is something like, it's a vertical alignment of 1 millimeter, the difference, and each time that the wheel passes this section, it produces an impact, a specific acoustic sound. So as you can see here, one locomotive with 9 coaches, almost overall 40 axles. So if we can see that on a rail joint, the question arises: can we also distinguish between good and bad track condition? But as we've seen and I've said before, each train creates a specific sound. A heavy train, a large train, and therefore you have to ensure same boundary conditions. You can also compare like with like. So the same train type, same superstructure. If you compare the signal of a wooden sleeper with a concrete sleeper, it is a different one. It will differ. And of course, same speed. You have to guarantee that the same speed is visualized in the signal. So as this is a very new data source, we have to validate it, what we analyze, and our results, of course. But how can we do that? We have the fractal analysis of vertical track geometry. What you can see here is the vertical alignment of the track. And if you split this signal into 3 different wavelength ranges, you can carry out component-specific evaluations. The short-waved range from 1 to 3 meters is an indicator for problems with the sleepers and for the fastenings and the rail. The mid-waved range, 3 to 25 meters, is an indicator for ballast breakdown, for the condition of your ballast. And the long-waved range gives you information about your subsoil, about the condition of your subsoil. If you want to know more about this, you can talk later, and you can read it in the paper. So let's take a look on 2 channels. Well, channels are always linked with a track kilometer. Yeah. So we have here 2 channels. The first channel, 54, it corresponds to track kilometer 126.33 and shows a very good condition. Concrete sleepers, new ballast, and indicates a track section with a good condition. Channel 46, well, you can see it here, ballast breakdown. Abrasion of the ballast, this is mainly due to the forces which are induced into the subsoil. So this is very critical, because normally a track deteriorates for 1 or 2 millimeters over a year. This can deteriorate over 5 millimeters, depending on the track volume, within 2 months. So this is very critical, this one. So can we see this in the DAS signal? Well, first of all, the raw signal of channel 46 with the bad track condition. You can see here, before the train approaches, it is a steady signal, and as the train approaches and is present in the channel, you can see that zigzag pattern. So what does it mean? Well, compared with the channel 54, yeah, it is different, but what's the difference? So has it something to do with the track condition? Well, again, let's make a spectrogram and see if there's a difference in the frequency between these two sections. So we expect that when the train passes a section in good condition, you can see it in the frequency in the spectrogram, but you will not have any peaks in the frequencies due to no specific impact of the wheels or the axles. So look at this. Channel 54 with a good track condition. Up to frequencies of 50 Hertz, there is noise. There's always noise in the signal. You can see also in this section the impact of the locomotive and the bogies. But compared to channel 46, you can see the impact of the first axle of each coach, because it creates a specific sound when it passes this section. As I've shown, DAS enables for a condition evaluation of track, and asset condition monitoring, what you understand under this term is track and turnout condition monitoring, ballast breakdown, weak subsoils, rail joints, and of course maintenance. Maintenance is a very hot topic for infrastructure managers, because most of the maintenance is outsourced and the maintaining companies hold the data in-house and they won't give it to the infrastructure managers. I've published this before. With this measurement method, it is possible to visualize each tamping action. So when the tamping machine digs into the ballast and lifts up the track, you can see how long does it tamp. And one of the last, nearly the last slide, what are the fields of application for the EIS? We are focusing on that. Train tracking is possible, as we've seen. Even train integrity monitoring, as you can see, every single axle is possible. And of course, safety and security. In Austria and Switzerland and in Germany, some of the systems are installed and they detect rock falls, landslides, and cable theft. So it is possible, but of course, it is not in the actual operational. It does not operate the whole time. And why not? Well, this system produces a huge amount of data. 2 hours of recording of 40 kilometers of track produces 180 gigabytes of raw data. Just raw data. You have to analyze it, which also produces another amount of data. So you have to store it. So you have to decide what kind of data can I delete and what can I keep. What is important for me? Well, I think in times of 4.0, digital twins and something like that, this should be possible to solve the problem. But it's not my part, it's part of the suppliers. And one important thing is that you can use any single mode fiber, which is already installed alongside the Rayleigh track. So there are no, it is not necessary to install other things on the track or beside the track, and there's no influence on the availability of the track. Thank you very much.